Welcome to classes on organic chemistry. Today's class is on biomolecules and it is for higher secondary second year and class number 19. The biomolecules, actually those who are the student of biology, they may think that there is some similarity on biomolecules, but this biomolecule which is included in the higher secondary second year is not simply as what you have read in higher secondary in biology chapter. So it is a special reference to the chemical aspect of biomolecules. So first of all, very simple things: living organism or living bodies. You can write living bodies also. Living bodies comprises of the lifeless substances which are very complex and arranged in well-mannered fashion or well-mannered way in the cell of the organism are called biomolecules. Examples are carbohydrates, fats, proteins, DNA, RNA, etc. So actually these are the things: carbohydrate, protein, fats, or starch, all these things, cellulose, all these things are lifeless substances which are typically present in the cells of the organism, maybe plant or animal living organism, and these things are called biomolecules. Living bodies composed of organs. Organs composed of tissues. Tissues comprises of cells. Comprises of cells organelles, and cells organelles comprises of biomolecules. So you have got a very simple idea on what are biomolecules. Now, out of these biomolecules, carbohydrates. Carbohydrates are nothing in terms of chemistry. I am defining optically active molecules of polyhydroxyaldehyde and ketones that can be broken into simpler forms. That means the compound which are carbohydrates, they are nothing but optically actives. There are some optical activity I will explain in a bit later on, and they have hydroxy groups, and that hydroxy groups are OH groups, poly in number, a lots, and comprises of aldehyde and ketones. There are some functional groups aldehyde and ketones along with hydroxyl groups. These are optically active. These are nothing but carbohydrates. Now, the main thing of carbohydrate is classification. Carbohydrates are classified into monosaccharides. Number 2, oligosaccharides. Number 3, polysaccharides. Let us first of all explain what are monosaccharides. Mind that monosaccharides are the substance or the molecules of organic compounds, biological compounds, which cannot be monosaccharides, which cannot be further hydrolyzed to smaller biological unit. You can't further hydrolyzed into biology. That is the simpler form is called monosaccharides. What are oligosaccharides? Oligosaccharides yields 2 to 20 number of monosaccharides on hydrolysis. Hydrolysis means when you hydrolyze in presence of acid or in enzyme, that oligosaccharides broken into different smaller units of monosaccharides or 20 to 22 to 20 numbers of monosaccharides on hydrolysis. Oligosaccharides. In oligosaccharides there are disaccharide, trisaccharide, etc. Now what are disaccharides? Disaccharides are the molecules, organic molecules, which on gives two number of monosaccharides of same type or different type. What are trisaccharides? On hydrolysis gives 3 unit or 3 numbers of monosaccharides. What are polysaccharides? Which on hydrolysis gives a large number of monosaccharides. So these are depending upon their reducing property. They are also called reducing, for example, reducing sugars and non-reducing sugars. Non-reducing sugars. Now, what are reducing sugars? Reducing sugars means in aldehyde or ketone, when they are the polyhydroxy aldehyde or ketones. They are optically active compounds of polyhydroxy aldehyde or ketones. So aldehyde, if they are present in monosaccharide or disaccharides, they reduce or failing solution. So that CHO group becomes COOH. That is CHO group means aldehyde. Sorry, monosaccharides or disaccharides having free CHO or CHOH. CHO is present adjacent to CHO group. One condition is there should be free CHO or CHO if it is to be reduced. If this compound reduce toluene and failing is these compounds have the ability to reduce toluene and failing solution, that is CHO or CHO should convert into COOH. These are mild oxidizing agent. Then these sugars are called reducing sugars. So what are the conditions? This is very important. What are the conditions of reducing sugars? A sugar should be termed as reducing sugars if they have free CHO or CO groups in the structure, and second, if CH or COO group is adjacent to CHOH group. Second condition. And third condition is a bit tough. You should know it. If in the disaccharides, there is now this point is a bit acetal form. If in the carbon OH and OR group is there and other R and H is there, that form is called hemiacetal form. And if in the carbon, if two groups are OR and OR, say 1 and 2, OR and OR, whatever may be these two groups, This is called acetal. If in the structure, hemiacetal structure, I will explain later on with a specific example. Hemiacetal structure is there, then this structure very easily rearranged into CHO form. Rearrange. If there is hemiacetal form, this form COH or an R form is there. Then if there is this form, then that form in equilibrium may be rearranged to enolized form CHO. And if there is any CHO, then CHO will reduce toluene phenol reagent to give you CHO. If you find ring structure, and the ring structure, if you get CHO, a bit later we will come. If you get in this way CHOH in the ring structure, then CHOH part again transformed into CHO, again rearranged into CHO, ring to open. A bit later you will understand. Glucose, fructose, galactose, ribose. Am I right? So minutely now follow. It's a bit tricky. Just you see glucose. Everybody of you know. Now let us show the CH structure. This is the open structure, open chain structure of glucose, open chain structure of glucose. Now here I write D-glucose. So many of you have a confusion to say how can you designate is D-glucose and L-glucose. This is actually nothing but one thing I am telling. L is related to configuration, small d and small l related to rotation, plus minus related to rotation, alpha and beta related to anomers. Please don't be confused with these symbols. When D and L nothing rotation or nothing to related to optical behavior, these are some configuration. You will understand. This is D-glyceraldehyde. This structure is called D-glyceraldehyde. Fact is that if OH is towards right, D-glyceraldehyde, this is the form, this is the structure with the help of which we can designate its configuration. If CH2 and number this carbon COH is towards right, it is D-glyceraldehyde, then we will tell it in glucose it is D-glucose. Now if that OH is taken towards left, towards right, then that structure is called D, that structure is called L. If OH is taken left and H is taken R right, it is called L-glyceraldehyde. So in terms of L-glyceraldehyde, if we now just change this one H and make it this, then this will become L-glucose. So DLL are nothing but the configuration, and that configuration is with respect to the configuration fixed DL-glyceraldehyde. Either OH is right, it is called D, OH is left, it is called L. So comparing the structure of glucose last to CH2 above this, that carbon we will compare that carbon with diglyceraldehyde. If it is diglyceraldehyde type of shape, it is D-glucose, and if OH is the left, it is L-glyceraldehyde, that will be L-glucose. Am I right? So this is all about the structure of glucose. Now you see, this is open structure of glucose. In glucose there are 6 carbon, so it will show optical behavior, anomers, it will show epimers, it will show isomers, it will show rotation. These are the behaviors we will not just compare with the open structure. Just you parts of chiral carbon, stereogenic center, that is carbon having different group or atom attached. So if you assume this one, so with this carbon OH, H and CHO, and whole this part is one part. 1 part, 2 part, 3 part, and whole part, 4th part is a different. So that carbon has got different groups or atom attached with it. So that is chiral carbon, that is stereogenic center, it is disymmetric. So optically active center 1, like this. So if you consider this one, this is 1, this is 2, this whole part 3, whole part 4. In this way, if you find, you will find 1, 2, 3, 4. 4 are chiral center. 4 chiral center, 4 chiral center, 4 number of chiral center. So it will show isomers 2 to the power n, where n is equal to number of chiral carbon is equal to 4. It will show 16 number of isomers. So glucose will show 16 numbers of isomers. We will not explain all this. Sometimes questions in entrance exam often comes, how many chiral atoms are there, how many number of isomers can be possible with the glucose, so that you can find yourself. Number 1. Number 2, anomers. That is, optical activity is due to the presence of the chiral center that have the ability to rotate the plane polarized light either towards right or towards left. That's why they have got the optical activity. So this is the first point. Am I right? Second point is isomers. So the formula is 2 is equal to 2 to the 4. 4 is the number of the chiral atom. 2 to the 4 equal to 16. There are 50 isomers. So out of this isomer, you will find out again isomers. Epimers are type of isomers, and anomers is another type of the link in cyclic structure. So let us come to anomers. Now what is anomers? We will a bit later come that it may have open structure, it may have cyclic structure. So that we will establish later on. If we assume this as a cyclic structure, now you see, we can draw the cyclic structure. So the way how we can write, first one was CHO, carbon 1, that is carbon 1. Through this structure we will draw in this way. I will explain the structure in a simple way, and you this way. You see, CHO, one H has come, and here from OH we have taken this here. There was CHO and there COH. That O has come here, and one H is here. So you see, this is one cyclic structure, and this cyclic structure, we will explain why we have done this. This cyclic structure consists of 1 2 3 4 5 6. Am I right? You see, each and everything is correct. This structure is basing on carbon 1, and that carbon 1 is called anomeric carbon. Anomeric carbon. Anomeric carbon means, here it is carbon number 1. Anomeric carbon means the carbon where there was functional group, and that functional group has been changed in this form in a cyclic fashion. That's why this is called anomeric carbon. Now, since OH is towards right, since in C1 OH is towards right, we have a bit earlier written in anomeric form we use alpha and beta. Am I right? So it is alpha. If OH is towards right, we designate is alpha, and it is from D blocus. The structure was from D blocus. OH was this. So alpha D blocus. Am I right? Alpha D blocus. Now I am not writing the next structure. Just you see, from that one, if you make it OH and make it H, make this change, then that structure will now become D blocus. So these two blocus are anomeric. So diastomers which has different form, stereoisomers, diastomers which have difference configuration at carbon for glucose are called anomers. Very important things, you please keep it in your mind. In glucose, where the configuration of C1 is different, and due to difference in C1 configuration of glucose structure, the two anomers appear. One is alpha D glucose, other is beta D glucose. If OH of C1 is towards right, it is alpha D glucose, and if OH is towards left of C1 anomeric carbon, that is beta D glucose. And these two structures are different in configuration at C1 for glucose, and hence these are called anomers. So this shows difference here. You write another, everything same. In carbon 1 and carbon 2, if you make difference, simple difference, then this structure and that structures are called EPIMERS. So epimers, not only this, epimers may also be, that is glucose, that is mannose, and if you make, say this is glucose, D glucose, if you make difference, here, if take OH here, H here, this is called galactose. Again these are epimers. So mannose, galactose are the epimers of glucose, but mind that there is no cyclic structures. There is no cyclic structures. So we have explained epimers are the glucose having open chain glucose having difference in configuration carbon. I am not showing any carbon number other than carbon 1, other than carbon 1 are called Epi with one of glucose and ring structure is there anomers. Other than one, if you make any change and if the structure is open, then all structures or change in the configuration in any other carbon other than carbon 1 are called epimers, but no cyclic structures. So we have got epimers, isomers, mutation. Mutation, beta glucose are found to be in rotation, and rotation reaches to a fixed from equilibrium mutarotation, that is alpha D glucose, open chain glucose, D glucose, I think it is 4. See, we have already explained D glucose and alpha in the anomeric form, that is at C1 carbon OH is towards right in cyclic structures, and if the specific that alpha glucose and beta glucose are always in equilibrium from open chain. One time open chain glucose is transferring to is converting to alpha D glucose, and other time it is transferring to beta D glucose, and specific rotation alpha D glucose is 111, and specific rotation or beta D glucose is plus 19.4, and open chain glucose has rotation specific rotation 52.5. So in the equilibrium condition from alpha to beta D glucose from open chain glucose, they always appear a fixed value, and this phenomenon of rotation of alpha to beta glucose is called mutarotation. It is called Pirano structure, and this is also called Howe earth structure. Howe structure. So pyranos, what is pyranos? The name has came from pyran, called pyrano structure, and this structure also called Howe structure. So now let us see 1, 2, 3, 4, 5, 6. Am I right? This is 1, 2, 3, 4, 5, 6. This is called alpha D glucopyranose alpha D. Why it is alpha? Let me just in a speedy way I am showing you. Just to see, you manually follow. This is 1, am I right? 1, 1, 2, 3, 4, 5, 6. That is CHOH. And when you written CH is equal to CH is, and from one hydrogen here, from carbon 5 one change occurs. In nanomers, carbon 1 and carbon 5 change. So here we have written H, we had written H, this is 1 number carbon. Am I right? We wrote in this way. OH. Am I right? So you see, C1 carbon means here C1 carbon means this CHOH. CH. Since OH we have written OH, right is below and this above. We have represented in this way. So one is this, right means below, left means above. In this way, 1, 2, 1, 2, 3, 1, 2, 3. Just you compare. 1, this is 1, this is 1, this is 2, this is 2, this is 3, 3. Am I right? So whatever is towards right, we have written below, and whatever is towards left, we have written above. This is the concept. This is called alpha D. That structure is alpha pyranose. Alpha anomers. OH is towards right of carbon 1. So this is alpha. D is from glucose structure D. And since it is glucose gluco, and C structure is analogy of pyran, so pyranose. This is glucose pyranose, alpha D glucopyranose. And just second one, OH is left, OH is taken left, this is beta. So if you take difference here, if you make it OH here and H here, that will be your beta D glucopyranose. So we have got two pyranose structures or Howard structures where this is in analogy with the pyran, hence this is called glucopyranose. Now sometimes you are asked that whether glucose is optically reducing salt. Yes, because in open stage structures there was C was free, but if you write closed chain structure, again we get CHOH structure adjacent to CHO. Am I right? And due to this structure was actually in equilibrium with open chain glucose structure. One times alpha, other times it gives left side beta. Very often these two are exchanging. So if CHO is not directly seen in here, but in equilibrium we get once open chain structure in CHO. That's why it is reducing salt. But here how can you explain it is reducing? You will explain it is reducing because in C1 there is CHOH group, and that CHOH group of C1 can very easily be made, can be made free in equilibrium. So very easily in equilibrium state it opens to give you open chain glucose. That CHOH groups become CHO. That's why we can get free. That CHOH groups can be made free CHO in equilibrium. That's why beta D glucopyranose or Howard structure or pyranose structure of glucose is again reducing salt. Open stage chain structure and glucose may be closed chain structure. How can you infer? How can you suggest? How can you prove? How we give you evidences? What are the evidence in terms of open structures and what are the evidence in structure cyclic structures? And this is glucose. Let us see what happens. Gives N-hexane open chain and right structure yourself. Now, if you ammonium hydroxyl groups, um, hydroxyamine. If you want to make this reaction, it is a special reactions of aldehyde group. What is aldehyde group? Aldehyde group is this: carbon 1, carbon 1 is this. This is carbon 1. Am I right? Carbon 1 is this. Carbon 1 is this. So in carbon 1, if you add in this in this way, so we have seen in aldehyde chapter that they very easily release just that one. So we get CH and CH double bond and OH, and other things all same: CHOH whole thing 4 and CH2OH oxide. Am I right? So what is the next one? Next one is bromine water. This is mild oxidizing reagent. So if it is mild oxidizing reagent, CHO C double OH group, other things will remain same. Gluconic acid. What is anhydride? H3 into O. Am I right? So CH3CO, that group will just replace uh, that H. You write. So you write CHO, CHO, and in H you write COCH3. COCH3 in place of H. And in next place CH2 is here, in place of hydrogen again you place COCH3. So 5 acetate, penta acetate. So last one was HNO3 concentrated. Now what's happened, you see, this is a strong COH and that is CHOH will remain same, and this is alcohol will become aldehyde will again become carboxylic acid. So we'll get this one. Now um, you see, if you assume it A, you take it A, glutonic acid. If you take A here, glutonic acid, and if you oxidize it, gluconic acid, gluconic acid, if you come to this one, that CH double OH, C double H, C double OH, nothing. This is same. Now what's happened? H2OH has C double OH. Am I right? Now you see the thing which we get from here. From structure 1, from this is 1, this is 2, and this structure is 5. Now you see what's happened. We have got a straight structure, a open chain, that is glucose. This is one evidence. Since glucose has reacted with NH2OH to give oxide, that means that glucose contains number 3 bromine water. One reaction of this one, it gives COOH, glucose gave COOH, and when COOH come, always COOH COH. Am I right? COOH always comes. So when it has oxidized to COOH, means there was COHO group. First we from equation 2 concluded it was CO group, but from third equation we got that it is COOH, means your initial compound contained CHO group. That is, that C ketonic group is nothing but aldehyde. So we have proved two things. One is that it has aldehyde. So number 4, apart from number 4 we get that replaced by COCH, that is 4 H from OH and 5th H from OH. So there are 5 numbers of OH group. So I have rubbed it. You see in glucose there are 5 number OH. From 1 OH, for 4 OH, H has been replaced by OCH3, and there is another H replaced by COCH3. So there are 5 OH in different carbon, and this compound is stable. That is, that OH was not in the same carbon. 5 OH was not in the same carbon. It was in different carbon. Now that when we made to react with acetic acid, nitric acid, so nitric acid is a strong oxidizing agent. So COH group became COOH, and CH2OH of glucose last again that converted to COOH. And on the other hand, in gluconic acid we get CH2OH, and that gluconic acid from original first. When that gluconic acid was again oxidized, which is from glucose oxidized, so COOH and COOH remain the same, but CH2 has converted to COH. That means there is one CH2OH group, otherwise it would have not been COOH. That COOH has come from CH2H. There is 1 degree alcoholic OH. Alcoholic OH, 1 degree alcoholic OH is there. So out of these 3, we see that it suggests the open chain structure. Though there was CHO group open in open state structure, but this glucose does not react with Skiff's base or Skiff's reagent, and also does not react with sodium hydrogen carbonate. Had there been CH free, it would have reacted with sodium hydrogen carbonate very easily, but sometimes it is seen that glucose does not react with this and this. That means CHO group is not free. That is, in anomeric form it has got cyclic structure. At penta state of penta does not react with NH. So earlier I have already shown you what is pentacetate. So that pentacetate should have reacted with NH2OH, because if CHO group was open, OH would have added this C. Am I right? So if CHO was free, then pentacetate should have reacted with NH2OH to give you CH double bond and OH structure, but it doesn't react. Means CHO is not free. It is somewhere in cyclic structure. That establishes the fact that glucose has also some anomeric cyclic structure. of fructose, the structure is you yourself write it. P fructose D this. If it is twice right, it is D. If it is twice left, it is L. Which L fructose? So we have seen there are CO group, and that's why CO group it is a reducing salt, but reacts with tolerance basic sugar with tolerance, but CO generally doesn't. But what's happened? That CO group, when reacted with tolerance, it is solution. Basic condition. Due to basic condition of the tolerance reagent, that CO group changes to CO in equilibrium due to the basic condition of tolerance reagent. That's why fructose is also a reducing sugar. So likewise, we can draw anomers of glucose. How can we draw anomers of glucose? Now it is a bit different. You see, that CH2 group, you just take it here, CH2OH. Am I right? Am I right? You make it H. This. You rub this one. Right? So you see 1, 2, 3, 4, 5, 6. OH is towards right. So this is anomer, but here carbon is 2 carbon. Earlier in glucose there was carbon 1, but in fructose it is carbon 2. Mind that this is the difference. Carbon 2. So what's happened here? We see this is alpha D fructose. Alpha D fructose. But when you change this carbon 2, if you write here towards side and OH towards left, as when the same, this would be B. So these are the anomers where there is difference in configuration in C2, hence we get anomers alpha D fructose and beta D fructose. So keep this structure as it is. Now go to the Howard structure, HHORT, or no structure. Structure has furan, 5-membered furan. So analogy to the furan, if you draw this structure, then this furanose structure. Sorry, this is furanose structure. So here you see CH2OH. CH2OH. From one will start. What's right OH? This is one. What's right OH? This is below. 1, 2 is 3. In 3 what? Towards right and left this is H. So from glucose there is a difference. In glucose we get OH below 3 carbon, there is a change, but in fructose we get OH above and this one will be OH, and this is same. You yourself count to here it is below towards side alpha E, and since the structure has come from, that is alpha D fructofuranose. This is alpha D fructofuranose. So if just you make the change here, you write OH here and CH2OH here and B fructofuranose. Very simple. Just you keep it in your mind. Again, this is reducing sugar. All monosaccharides and disaccharides are using sugars, except question very often comes. Now what are the examples? Mind that, you keep it in your mind, is very important. Sucrose, except sucrose, all monosaccharides and disaccharides are reducing sugars. Now it's monosaccharide on hydrolysis. And these two monosaccharides may be same or may not be same. So one example is maltose, another is lactose, fructose and glucose, and this beta fructose. And maltose on hydrolysis gives both glucose and this is beta galactose beta. So all hydrolyzed product I have shown you, and fructose and combine, that combination occurs to link when glucose and this glucose sucrose will get fructose and glucose. Fructose is B and glucose is alpha. So how these two will combine to give you, that will gives fructose, glucose carbon 1 and glucose carbon 2. You write glucose first, so you not be confused. You write glucose, this is alpha, and fructose, that is beta. So alpha glucose C1 and beta fructose C2, there will be linkage, glycosylic glycosidic linkage will coming later on. And when glucose alpha and glucose alpha are joined, we get maltose, and that maltose carbon 1 of 1 glucose alpha and carbon 4 of other glucose delta glucose structure will combine to give you this. And glucose beta and lactose beta, they will combine carbon C1 and carbon glucose alpha and fructose. The structure is one, two, 5, 6. This is glucose alpha, alpha D glucose. This is fructose. CH2 OH H, but here OH above H OH CH2 OH H 1 3 6. That is actually fructose, but we need beta fructose. So here that part will be OH here, and that will be CH2OH. So we need C1 and C2 connection. At the very beginning I have effaced it out, right in this way. Two, 1, 2, 3, 4. This is 1, 1. This is 2, 1, 2. This is 3. OH above. This is 4. H above. OH this. Am I right? So this is 2 fructose C2 and glucose C1. So C1 C2 is combining. Oh, there was OH. Sorry, this is OH. So out of this, water getting here. I'm not writing all this structure of carbon 1 is H, and here bond O, here CH2OH, and this is 2. Other structure will remain same. I am not writing. Here you have got this structure. Am I right? This one. So my main intention is to get this. This is called glycosidic linkage. The linkage between two monosaccharides through oxygen with the elimination of water is called glycosidic linkage, and this is sucrose sucrose is not reducing one. That sucrose is not non-reducing. It is non-reducing because here this group, this carbon and that carbon, these two carbon are called acetal form, and that carbon and that carbon acetal. So if there is hemiacetal, what was hemiacetal? Hemiacetal is this structure. We should get CHOH. So nowhere in this carbon CHOH and nowhere in this carbon CHOH. All the carbon are getting OR acetal form, and due to this form, this rotation is restricted, and due to this restriction rotation, it doesn't form in any CHO open structure. That's why it is non, because of acetal form or absence of hemiacetal form. Hemiacetal form, this form. Here, out of this carbon, we do not get this form. If there was this form, out of this form, we could have written forward. Here, and that OH and H as alcohol will go out. As alcohol, ROH will go out. We are getting only one carbon, C double bond O, and H R dash. We are getting aldehyde. Am I right? So had it been these two carbons were hemiacetal of this type, so in equilibrium it would have rearranged to CHO, HO like this. ROH vanished out as alcohol. R dash H double bond O, R dash H double bond means aldehyde groups they are open. So we did that would have instantly react to Tollens and Fellings to reduce Tollens and Fellings. Hence there is no option left. It is acetal form, and the restriction is rotation is restricted, so we can't get CHO form. Hence sucrose is non-reducing. So out of this is last invert sugar, very famous question of Knox. I you see sucrose is in general it moves the light plane polarized towards the right, and on high it gives glucose and fructose. Glucose and fructose. Glucose is dextrorotatory, it rotates 52.5 degree, and fructose is laboratory minus 90. So you see labo is more than dextro. So sucrose in the mixture of plus 52 to minus 92.4 individual, that is totally we get total mixture is minus. So from positive rotation to final a mixture which have negative rotation, and this phenomenon is called invert sugar. Hopes you have find the class most interesting, and I will come with the next very small part of this left behind in the next class. Within 2 or 3 minutes I will complete this one.